Okay, good morning everyone and welcome to today's webinar. Today we're going to be speaking about SOLIDWORKS Simulation and discussing some of the considerations for meshing in that finite element analysis tool. And my name is Glenn Whyte, the Director of Technical Sales here at Hawkridge Systems, and been working with the SOLIDWORKS Simulation tool for about 12 years now. Now, before we get into the content, and as we still have a few people joining us here, logging on, I want to give you a quick rundown of the GoToWebinar interface that we use for these sessions. The GoToWebinar interface, everything you can do with it is controlled from the GoToWebinar control panel. It's a little bit updated from the screenshot you see there, but if you don't see it on your screen, you want to look for an orange arrow, and that will allow you to expand that panel, and this is your primary mode for interacting with us here. Because of the number of people we have today, and we have a great audience today, we have everyone muted by default. There are two options for accessing the audio. You can either use the mic and speakers on your computer, or you can dial into the telephone. If you're having trouble with one of them, I'd encourage you to try out the other one. And the screen size that I'm presenting right now is what I'll be using throughout. There are controls in the view menu of the GoToWebinar screen to adjust your scaling, so you can see that. Now, if you want to interact, and I would really encourage you to do so, the question panel is your primary mode for doing that. I'd love you to ask any questions you have or any points of clarification. Our topic today on meshing is a huge topic. We're only really going to be able to cover some core elements of it and some tips and tricks that I've prepared for you guys. But if there's a particular question you have, I'd really encourage you to use that question panel. There will be plenty of time for us to dig into some of your specific problems or questions or things that you want clarification on. And before we jump into the content, my last housekeeping element is to just check through a poll that you guys are seeing and hearing. So we'll start with seeing. If you can see a poll on your screen, you'll be able to tell me if you're able to see or if you were able to see my screen. And we have a unanimous success there, so that's great. And then just a question about my audio, and you're free to let me know any feedback you have on that. And that is also coming in really positive. Okay, so I think we're ready to go. So as I mentioned up front, we today are looking at the meshing elements of SOLIDWORKS Simulation. Again, my name is Glenn Whyte, one of the engineers here at Hawkridge Systems. Now, just to put this in context, here at Hawkridge Systems, we're primarily known as a SOLIDWORKS reseller. But SOLIDWORKS these days goes so much deeper than just the CAD tool. You know, there's tools for electrical design, PCB design, there's a data management suite, technical communication tools, composer inspection, model-based definition. On top of that, we also carry CAMWorks and the new SOLIDWORKS CAM product released in 2018, as well as 3D printing tools, 3D printing machines from HP, Markforged, and Union Tech. But we're here talking about analysis today. So if we dig into the analysis suite, we've really got 5 different analysis technologies that we feature now. SOLIDWORKS Simulation is our designer level structural analysis tool. SOLIDWORKS Flow Simulation is a really powerful computational fluid dynamics, or a CFD tool. SOLIDWORKS Motion Analysis, kinematic analysis for assemblies based on the atom solver. SOLIDWORKS Plastics is for injection molding. And Abacus, Simulia Abacus, as well as some other high-end analysis tools, is expert level structural analysis for complex problems. A tool we brought on board several years ago. But what all of these things have in common, for the most part, is that they're design validation tools designed for all users. You don't need to go get a PhD in FEA or CFD to correctly apply these tools and get valid answers. They are all, to some level, directly integrated into SOLIDWORKS. So if you make a design adjustment, there's a very smooth, quick process to analyze the effect of that design adjustment. And here at Hawkridge Systems, we're a single source solution. Doesn't matter what analysis product you have, you give us a call at the same line you do for technical support for your CAD system. We provide training, we provide consulting services if needed. It should be a one-stop shop for your analysis needs. And just drilling into the structural analysis a little deeper, there are several packages available for the SOLIDWORKS Simulation Suite, starting from fairly straightforward stuff on the left to more complex nonlinear and dynamic analysis on the right, and even further to the right, the Simulia Abacus tool with the two solvers that has. But what are we talking about today? Today, we're talking about meshing. Meshing is a fundamental component of everything, well, of most analysis tools. There's a couple of new meshless technologies that have been bumping around in the market. But for a tool like SOLIDWORKS Simulation, it's a fundamental component of every single analysis. No matter what type of analysis you're doing, if you're doing structural analysis in SOLIDWORKS, you're doing a mesh, whether that's exposed to you or not. And meshing is essentially just, the alternative term for it is discretization. It's the process of breaking down real 3D geometry, for the most part, into a consistent shaped element that we can perform stress calculations on. Okay. And in SOLIDWORKS Simulation, we have three fundamental element types. Triangles, triangular shell mesh for thin parts. Beam mesh, it's a two-node line element for things with constant cross-section, weldments, those sort of things. And for everything else, solid tetrahedral mesh. We intentionally limit the scope of the elements that are available to really, so that we limit the scope of the elements available to ones that we can provide really robust meshing algorithms for, right? There are pros and cons of different types and other analysis packages like Abacus. You'll find brick/hex elements. You'll find a variety of different items. Everything in SOLIDWORKS is a tetrahedron that's solid. And so we're really going to focus in on those SOLIDWORKS simulation tetrahedral elements for the most part in this conversation, just to narrow the scope of what we're talking about today. Okay. So that tetrahedral mesh element, by and large, when we talk about this, and we talk about the element we're using in SOLIDWORKS, it's the one on the right, the high quality element. This is the default element that is applied to SOLIDWORKS geometry if you try and run an analysis on it. It is a second order element, so it has parabolic edges, right? So they're not straight lines, they can map to curved geometry. And it has 10 nodes, 4 nodes at the corners and 6 mid-side nodes. In shorthand, you might see this referred to as a TET10 element. And each of those nodes has 3 possible degrees of freedom. It is free to move in 3 translational directions at each position. And so we say it has 30 degrees of freedom per element. That's basically how many displacement calculations are being performed per element. Like I say, it's the default. It's the one you use if you don't go mess with anything. There is another version of this element. In the software, it's labeled as a draft quality element. You'll see a checkbox in the meshing window, and I'll point it out when we get there. This is a first order version of that element. It has straight sides, so it won't map to curved geometry. There's 4 nodes, only at the corners, and it only has 12 degrees of freedom per element. Now, that means it's capturing substantially less stress information for the same size of element, but the counter to that is that it solves really quickly. So I typically use the draft quality element for testing purposes. If I want to see if I've got the right restraints in my model or something like that, I will use that draft quality element just to fail faster or make those mistakes more quickly. If you've heard kind of FEA shorthand that tetrahedral elements overpredict stress and bending or underpredict different things, most of the time that tetrahedral element that's being referred to there is a first order element like this draft quality element. To be honest, they're pretty bad. I would not take the results from a draft quality element and show them to anyone. Okay, but some great studies out there that show that in the majority of situations, that high quality second order tetrahedron is going to give you a result within an acceptable accuracy the vast majority of the time. And that's really why we picked it as our core element in SOLIDWORKS Simulation. The other reason we picked it is it's really easy to write. Well, not easy, it's the wrong word, but there are very good meshing algorithms available for the tetrahedral element. So while you have your element, it's no good to you if you can't get it onto your model. If you can't map it to your model, you really can't do an analysis. So the algorithm that you use and the way the software applies that is really, really important. And in SOLIDWORKS, we now have 3 mesh creation algorithms. One we call standard, that's the one we've had forever. Curvature-based, which we introduced in about 2008, so it's been around for a while, which looks at the local curvature of the model and scales the mesh to match in that area, and a blended curvature model, which is relatively new. So let's explore this based on a piece of geometry. And I've got to admit that this geometry has been selected solely to be hard to mesh. It is a little artificial, but it will do the job. And some of the things that make it hard to mesh, we've got some very narrow sliver surfaces. We especially as you get into here, there's a lot of stuff going on, and these holes with irregular spacing between them, and some cross throughs, just creating a whole bunch of narrow gaps and different things. Okay, so if you create an analysis, you go to simulation and create a new study. Let's do that. start with a static stress analysis. We go to create a mesh. First of all, in this advanced section, you'll see this toggle here to turn on the draft quality mesh. If you leave that off, you'll get the default high quality mesh that's going to give you good elements, good results. So that's fine. So now we've got these three options here, and the software is going to estimate a default size based on the general size and volume of the object. Okay. The standard mesher, in essence, is going to look at every single face in the model, right? So that's a face, for example, and try and map a 3.64 millimeter element to it. If that face, well, in this case, this has a radius of 0.5 millimeter, that face can't fit that element, it'll try and skew it within a tolerance. It'll try and make it fit. We can certainly map to faces that are smaller than this value, and obviously we have control as well. But at some point, if the face is significantly smaller than this value, it'll just give up and say, I can't do it. Right? The curvature-based mesher is taking a slightly different algorithm. It's looking at the local radius of whatever it has, and based on that local radius, trying to apply a cell size that's somewhere between this top value and this bottom value. So you can see immediately we've got kind of twice the scope, where we've got a much wider scope, and it's trying to map 8 elements to a circle. Right, that's kind of, as it sees a quarter round like this, it'll try and map 2 elements across that, which is a good rule of thumb. And we'll do some other stuff. The blended curvature base mesh is kind of an alternative to that, you know, still looks at the curvature, the local curvature of things, but we'll try to do a better job of smoothing big broad areas to give you less mesh overall. Okay, so I've taken this geometry and I've tried to mesh it with all 3 of those approaches. So the first one here, when I tried the standard mesh and I hit run with the default value, it fails. It says I can't do anything with this geometry. This is no good to me. Right. In order to get a valid mesh on this model, I had to manually go through with trial and error and apply a local mesh refinement to 133 unique faces. Okay. I also had to manipulate the global size down a bit smaller just to even get it to fire to a 2 millimeter general size. But I got it done. I think I can show mesh. And so what you'll notice with this particular mesher is everywhere away from those controlled areas is a very regular, even size. Right? See these ordered rows, and then as we get into the areas where I had to refine, you know, you've got a bit of a transition going on in those zones, but that's all being applied manually, essentially. Okay, otherwise, did get a mesh. I can go run an analysis on this now. With the curvature-based mesher, I just left it at the default and hit mesh, and I'm brave enough to do this one live. But maybe I shouldn't be. Oh. And so, you know, one click, I've got a mesh. You see the variance here. I've got a big broad curvature here, and these are big cells. I've got, smaller cells around here. It's mapped to this very thin piece of geometry up on the top here. It got it done, without any modification or adjustment. Now, this doesn't mean this mesh is good enough for an accurate result. We'll talk about that in a minute, but we did get it done with that curvature-based mesher. It's a lot more flexible. Okay. And the other one I tried here was the blended mesher, which has very similar settings. And, my takeaway from this one is it's just a lot more kind of organized, right? It's kind of got the organization of the standard mesher and these nice regular, adjustments. Kind of made a mess of these holes, but that's fine. With some of the curvature-based elements, it's kind of somewhere in the middle. So, but some of the other considerations there is how long does it take and how much mesh does it generate, right? So if we compare kind of some of these fundamental parameters, starting with the standard mesher, the big call out here is that it took me 35-ish minutes to poke around and figure out which faces needed to be meshed, with me going through and trial and error processes to get all those mesh controls in place. So that's the big standout there. The standard mesher has very limited usage of multiple cores on your CPU. So it takes about 36 seconds to process that mesh. And with all that mesh control, I end up with 110,000 cells. The curvature-based mesher is very good at using multiprocessor computing. Runs in 16 seconds, one click, it's done, right? So my total cycle time is the time it took me to wait. 71,000 elements at the default, right? Because it's only refining mesh where it needs to, where there is high curvature. It's got a slightly higher percentage of highly distorted elements, but I could go fix those if I wanted to. And then the blended curvature, I kind of think of this as my really big hammer if I've got a really challenging meshing problem. It doesn't use multiple cores very well, so it is slow, the slowest of the group, but it will generally produce the least cells. So if you're in a very big, complex problem, you're going to get a smaller result, a smaller number of cells. That may not be good enough for accuracy, but it is what it is. So my recommendation to you to select one of these is make the curvature your default. It's more efficient, it generally does a pretty good job, but save the blended curvature for if you're really having a tough meshing problem. Okay, and you can flick to that, it'll take you longer to get that mesh done, but it might keep your cell count down. Right, so there's a couple of great questions that have come through. And so let's pause for a second to take a look at those. I'm just to see the context of the question, I'm just going to respond to them here. Joe asked a great question. How do we know what percentage of elements are distorted? And that's a very good question. The way you get to that is by right-clicking the mesh and going to Details. You get a little summary. And this is also where I've got the element count from. But you see here that 80.9% of my elements have an aspect ratio less than 3. So that aspect ratio is more complex than this, but I think of it as like the longest side divided by the shortest side. And a perfect element is equilateral. All 3 sides are exactly the same. Well, yeah, all tetrahedral sides are the same length. So 81% are pretty even, but 0.468 have an aspect ratio greater than 10. They're highly distorted. Okay. If you want to know where those are, there's also the ability to create a mesh quality plot to plot the aspect ratio, and boom, that's where those components, that's where those distorted elements are. You know, if you're concerned about that, and you should only really be concerned if you have distorted elements in an area of high stress. If you've got both those things in place, you may want to go look at a mesh control in there. So that's one question. The second question here is from Nicholas. Thank you for asking. It's about the other parameters that are available here in this plot. In general, based on the curvature, the first cell here is a maximum size. All right, so my big broad areas of curvature are probably getting somewhere close to a 7.2 millimeter cell. The bottom number is the minimum element size. Areas of very fine curvature are probably getting something close to that. These aren't hard limits. There's a tolerance to it all. How many cells it's trying to map to a circle. So we should see, if we hide that plot, should see, you know, sort of two elements across. I'll show the curvature one. Two elements across a half round or a quarter round, right? So there's two rows there. That's what we're expecting. And the last one here is the growth ratio. And basically, that says that's the rate at which the cells get bigger. So if we've had to use let's go to one of these circles. Whoops. If we'd have to use a very small element to fit in this round, the next row of elements will be 1.6 times bigger, and the next row beyond that will be 1.6 times bigger until it equals the global size. Right, so that's kind of the increment. Okay. And while we're here, we'll just wrap up. Two more questions. Good question from Tom. What is a good rule of thumb for element size versus feature size? In general, you know, there's all these FEA rules of thumb, 2 elements across a fillet. But it all comes down to you don't sweat it if there's no stress in that area. Right. So we'll talk about convergence in a bit that will ultimately prove out those rules of thumb, and you can start applying that technique. There is a good question here from Ross. He asks, when does this distortion, when is that a problem? I would say over about, if you have more than 5%, maybe just to throw a number out, highly distorted elements, that could be, you know, an issue. If you have highly distorted elements in areas where there's no stress, it doesn't matter. All right, it's when you have those two things combined that you want to think about it. And the ultimate rule is make it finer and see if it changes. And then one last question from Jason here, who's asking if the ratio applies to a mesh control when you manually adjust the mesh, and it absolutely does. It's defined here. Okay. So thank you all for those. But let's move on. So if you want to share some more questions, we'll pick them up next time we have a minute. Okay. So this is a part. Well, that was a part. What about an assembly? You know, what happens if we put those things together? Because that makes things a little more complicated. All right, so if we jump away from this model, and just to start with something really simple, got the world's simplest two-part assembly here with block 1 and block 2. But block 1 and block 2 share an interface that's a glued or bonded interface. And what happens at that meshing interface? So what happens at the interface between two parts is controlled by a setting that buried somewhere you may not expect. It's under Connections, Component Contact, Global Contact, and in here, there's two options for compatible mesh and incompatible mesh. What does that mean? Right. So, and this is the only place this option exists. A compatible mesh tries to exactly map the nodes from one component to the other. Now, to make this really obvious, I'm meshing the top component with a very fine mesh, the bottom component with a coarser mesh. So when I do look at the mesh for these, you can see we have that difference. But look what happens at the interface. Those nodes always line up perfectly. Okay. To the point where if I was to hide the top component and show the mesh again, you will see the imprint of the top part on the bottom part. The compatible mesh is the default. Now, you know, traditional FEA will always tell you that a compatible mesh is needed for accuracy, or it's the best case for accuracy, and it is certainly the best case. Also, it only applies if the parts are bonded. If this is a no penetration, a sliding contact, it's going to be incompatible by default. So what do we mean by incompatible? Well, in an incompatible scenario, which is just that same spot, an incompatible scenario, the two parts are meshed completely independently. There's no correlation between those things. Okay, if I was to hide the top part, the bottom part is going to look exactly the same under the component as it does everywhere else. You know, traditionally this would be considered bad or non-desirable, and in this case we have a very large difference between the sizes. This is really not desirable. But in this scenario, when we solve this analysis, an incompatible meshing will apply some secondary calculations, some what are called mortar bonding calculations, to create a match between those mesh components. And those calculations have got better and better over time and are better now than they ever have been. So to just prove that out a little bit, I've actually run these analyses. Right, so this first one is a compatible mesh. Okay. I've got a very sharp point on this. Just got a nominal load pushing on it, fixed here. But you can see kind of the stress distribution through these. I will call out that as you're, if you're ever looking at stresses between two components, there's this option that SOLIDWORKS loves to turn on by default to average the results across the boundary for the parts. That's not really real. It kind of gives you these, notice how the high spot has kind of jumped up off the point. That's not where it's occurring. So I generally recommend turning that off so that it's not, you know, doing an averaging calculation across that interface. Okay. So that's a compatible mesh. It's probably the best case. Can run an incompatible mesh. Can run the analysis. Oh, actually, I already have it solved. Anyway, solve it here again. It's going to do a pretty good job with one caveat. Oh. I'm just going to have to grab that model again. The caveat is there are two options of what style of incompatible analysis incompatible mesh you would like to use. And I will recommend one and warn you over ever trying the other. Sorry. So the option that I'm referring to lives here, right? In the properties of the study, in the solver options, under options, here, incompatible bonding options. The default is this one called automatic, which will either use basically a terrible calculation or a good calculation for that merging of nodes underneath that area. If you pick automatic, 90% of the time it uses the accurate one, but sometimes it'll go back to the simple one and you will get the wrong answer. So that's one that I always recommend setting to more accurate. It says it's slower, but the results are pretty bad. So what's the point of a fast result that's wrong? Right, so this is the more accurate result here. You can see you should get a little bit of a different result. It's not as good as the compatible. We have big differences in mesh size, so I certainly wouldn't recommend that overall. But it's relatively smooth and it concentrates the peak load at the corner. The simplified incompatible bonding, is blotchy. It's got these weird spots in places where there shouldn't be stress. It's just not good. So I would strongly recommend staying away from that simplified calculation. I think it's only still in the software for legacy support reasons, that if someone wants to mimic an old calculation, but it is something to steer away from. But the question that comes up here is like, well, why incompatible bonding at all? Why is that even an option? And the reason it's an option is forcing compatible bonding can sometimes impose a limitation that means you cannot get a mesh to compute, right? So basically, when we're meshing this as a compatible model, it's got to mesh this zone that's not underneath the object, and then separately mesh the zone that is underneath. If these two components, and I think I can move them, yep. Right, if I was to create like a very small sliver face here, my chances of getting a mesh element on there are probably pretty poor. Whereas incompatible doesn't care about that at all. In fact, you'll notice that one of the first options for a failed mesh is to just try the thing again with incompatible mesh to see if that makes a difference. And in most real-world scenarios, the incompatible mesh calculation does a pretty good job of being accurate. The other thing, compatible mesh requires that all the mesh components are meshed at exactly the same time. I can't do anything sequentially. Whereas if I'm meshing things incompatibly, as we'll see in the next example, I can take a sequence through where I mesh some parts and adjust others without having to remesh the whole thing. So that can be really, that can be a good little process. So, okay. So as I say, that incompatible mesh more likely to create a successful one, but just know you're doing another calculation. So we'll keep going here. The other thing that's worth considering when you're looking at an assembly is to think about the types of geometry you have. When SOLIDWORKS meshes things, or when you create a study on an assembly or a multi-body part, it does some things out of the box. It looks for special geometry cases. If it sees sheet metal, It'll create a 2D shell mesh. It'll treat it as a surface. And we'll do that automatically. If it sees surface geometry, it'll make that a shell mesh and throw it into your model. This can be problematic if you used surface geometry to maybe build up the shape of your part, but it was kind of construction geometry. You're going to want to delete that out or exclude it from the analysis. If it sees a weldment, it's going to throw a beam mesh on it, and everything else it finds, it's going to make a tetrahedral mesh. But none of these choices are permanent, right? They're all editable. So I've got this kind of Frankenstein part here that's got a block, 2 blocks, sheet metal, a surface, so that's only 2D, has no thickness, and a weldment, and they're all kind of jammed together. By default, the software says, hey, I found some sheet metal, I found a surface, and somewhere in here, I found a weldment, and the icon reflects that. Weldment and surfaces are simplified representations, but I can right-click any of them and say treat as solid, and it will mesh and analyze the true 3D geometry of the part. Now, it is pretty smart. When it does the sheet metal, it'll automatically recognize contact between components. So if I mesh this, what's it going to let me? No. Mesh this one. Right, these two parts have a little bit of an offset between them because it's put that at the mid plane. But that mesh, that contact will be respected, and we'll do that automatically. Same goes for the weldment component, which is nice. But why do we take advantage of things like shell and beam mesh? It's because they are more efficient, right? If I was to mesh this Frankenstein geometry with all solids, right, so everything is meshed to its true shape, right, so I've got a mesh element across the thickness. It's highly distorted, so it's probably not a very good result. Same goes for this guy. It works out to roughly twice the elements than if I use, shells and beams, which is what I've got here. One of the downsides in shells and beams is that you've got these simplified representations of the geometry. But a few years ago, we got a switch to map the stress and displacement results to kind of a representation of the real geometry. And so these things now have, a thickness. And so that can be better for communicating your result. But I would say to always review your model for things that are particularly shells, thin, constant thickness, put a shell on that, and you'll see big improvements in performance and often in accuracy as well. Okay. So the last piece here is, this is probably the most common issue. Before the curvature-based mesh was as strong as it is now, it was a bigger issue, but the most common complaint we'd hear of the technical support is I tried to mesh my model and it didn't mesh. What do I do now? And we have a little sample model here. Let's go to this one. Right. I haven't really prepared this model for FEA yet. I've got things like nuts and bolts modeled in true shapes. I've got the hexes on my screws still in place, all the stuff that we generally wouldn't recommend. But anyway, it's a good example. If we hit mesh on this model with the standard mesher, I get 11 parts that fail. And in fact, let's do exactly that. Standard meshes, standard size, hit mesh. About 56 seconds later, I get 11 parts that fail. Now the software will guide you through, and already that red is something you learn to fear. So the software does have an approach that will guide you through kind of a correction to that. I like to know how to do it myself before I take advantage of any of those regular tools. So this is the approach that I advocate before you activate any of the automated tools to help you out, right? And it's all about, you start by checking your model. Here's my 11 things that fail. We'll talk about the diagnostic in a sec, right? So there's parts just missing, they didn't mesh. Check the model. I like to go to the Evaluate tab and do an interference detection. The software will mesh interference, but sometimes it'll cause it to fail. And if you're running an analysis and the interference is not intentional, you're trying to model a situation that doesn't exist in real life. You know, there's some situations that are intentional, like shrink fit or O-rings or things like that. But otherwise, I like to know if I have interference, so I run that. The other thing I always do, tools, evaluate, check. This is going to do a consistency check. Do I have valid solid geometry? If I brought this over from, Creo and it didn't knit properly on import, it will never mesh. You can troubleshoot it for years, and if you don't have an actual solid, it will never mesh. So, and I have troubleshooted some of those models for years, and it wasn't fun to find out hours later that I had an import error that I took 30 seconds to correct. The other question I haven't put here, but I asked myself, is do I need this thing? Do I need the Phillips slot on my screw there? Is the thread on my bolt important to the strength of this object, or can I represent it with, say, a bolt check? But if I've decided that it is necessary, what I typically do is I go grab the thing, and the knuckle here was one of the things that failed, and I pop it open in its own window. Okay. I create a study, new study, and I try and mesh the thing on its own. Might need to pick an alternate size, but this thing meshed quite successfully with the default size of 9 millimeters. I know that with no other parts in play, this thing will mesh with a 9 millimeter mesh. So now I take that information back to the assembly and I say, oh, well, if I apply a mesh control, and notice here, a little trick here, if I pick a face from the screen, I'm only going to get that face of the object, but if I drag a box around it from right to left, I get the whole part. It's a little trick for you. And so it's going to mesh the entire body at a finer resolution. And does that get it done? Let's find out. The piece, so that often works. The situation when it won't work is if the connection between parts and the requirement of a compatible mesh is creating an interface that it's unable to mesh. But I believe that adjustment to that knuckle was good enough to get the knuckle done. And so then you can then repeat the process for all other parts that failed, right? So the knuckle, moving that control down to 9 millimeters was enough to get that done. And so if you're like really trying to be very regimented about that, that's a process there that you can go through. While we're on the screen, and like this will always work. It might take some time, but being very diligent and working through this process of applying mesh control and improving it will always work. There is also, well, just to come to a quick question, Nicholas Hunt, I mentioned a bolt, removing a bolt and applying I said bolt check, but I should have said bolt connector. There's a technique. We can take something like this bolt, remove it from the assembly, and replace it with a feature under the bolt, under the connections bolt. Basically say I've got a countersunk that's connecting this part to this part, and it will create an analysis construct, some beam elements and some pretension to replicate the action of that bolt. I'd recommend checking out, I think if you just type in the help, simulation help, or if you go to connections bolts and hit the help icon, there's some rich discussion of that stuff in the help file. Maybe a topic for another day. Ross has asked a great question that's relevant to what we just did. Because we applied a control here and then remesh the whole thing, it'll keep the compatibility between the components. Which one did I do? This one. Right, so faces that touch that knuckle, got a bit weird on me here, sorry. Faces that touch that knuckle will now have that 9 millimeter mesh mapped to it, right? So it's maintaining its compatibility. There's another workflow that's different, right? And so this is just the same model with no adjustments yet. Okay, so I can hit create mesh and we'll see how it goes. It's going to work. Let's go back to this one. Sorry. I will just undo that change there. So if I do apply mesh control and remesh the whole thing, it maintains compatibility. So that's important. We'll just let this go here, but the software will also offer you a mesh troubleshooting diagnostic. Right? The first thing it'll say when it fails, and it'll come up here in a second, is, hey, do you want to try and fix this? If you use this approach, what it will do is it's going to offer up some options here for how to fix it. It'll say, hey, do you just want to try incompatible mesh everywhere? Or do you want to add some mesh control? If you mesh control from this interface, it will only adjust that individual part and it will force an incompatible mesh. Right, so if you use this diagnostic and you say, you know what, I just want to modify the knuckle, right, wherever it is, boom. I just want to put mesh control on this guy. Now it's going to just remesh this guy. It's going to do it incompatibly, which is great for getting it done. But you have imposed that incompatible mesh now. Okay, let's move on. We are running a little long here, and I apologize for that, but we got one more kind of key point that I want to cover. And that is everything we've talked about so far is about getting a mesh onto a model. And we looked at some basic things about distortion and those sort of things. But everything we've talked about today is about getting a mesh onto the part. We haven't yet really talked about whether that mesh is good enough for a good result. And the dirty little secret of FEA is that if your mesh isn't good enough, your result's garbage. And a lot of the expertise you build up over time is being able to very quickly judge, based on a given scenario that you might have seen before, whether you've got a good enough mesh. But if you don't have that experience yet, you can fall back into some routines to always make sure. And this is the ultimate trade-off, right? We could all throw 10 million elements on every model we do and almost guarantee a decent answer. But there's no sense in waiting 4 hours for every analysis run if you're just maybe doing some early stage investigation. So I'd encourage you to be smart about the purpose of your analysis. Do it. But we've got a simple analysis here, a little bracket under some loads. And the other one will do. And I can go run the analysis. And I'm going to start off here right at an extreme level. If I go run this analysis with a fairly coarse mesh, a couple of distorted elements, it predicts a peak stress of 107 megapascals. Great. A couple of things I look for. This result looks blotchy. Right? It's got these weird kind of stripes to it. That's never a good sign. But in general, once you've got a result from an analysis, you should always try to improve it or try to validate it. So I would generally go in and refine the mesh a little bit further. In this case, I've made it twice as dense and run it again and see if my 107 megapascals is holding up. And in this case, it has jumped up to 114. That is roughly a 7% increase. 7 megapascals increase, it's about 100, so 7%, calling it. That's pretty significant. So we try again. Create another mesh, and maybe go half as big again. We run it again. Notice we're taking longer now to process this. But in my head, whether I do this formally or not, I'm always questioning the result, and I'm always trying to get a couple of data points to prove to myself kind of how stable my result is. Whether I do it formally or not, I'm always trying to build, an internal table that looks like this. First column is the mesh size. Second column is the degrees of freedom, the number of elements in this, number of stress calculations in this model. I then look at results. I can look at the displacement result, which will not change very much. Displacement, the distortion of the model is not very mesh sensitive, but stress is. It's varying 20 megapascals, 20% across these tests. And the solution time goes from 2 seconds to, I don't even know what that is in minutes. I did run out of memory in this top one. For the solver, I'd selected, there was too much memory for my system. The software wanted to switch me to a different solver that would have been more efficient, that would have been a lot faster, but just for consistency, I stuck with the same solver. So if you plot that out, horizontal axis is degrees of freedom, vertical axis is stress, you often see these curves that have this kind of knuckle to them. Whoops. Right. Where, you know, between 100,000 cells and 700,000 cells, I've got a variance of like 3 or 4 megapascals, 3 or 4%. That variance is probably going to be less than a bunch of the assumptions I've made in putting this analysis together. So the lowest model that I'm happy with that kind of gives that result is my most efficient one. That might be the one I try some different design alternatives on, somewhere down in here. I want to feel really confident I can use this one, but it's going to take me longer each iteration. Now, in this particular example, I've meshed the whole model. A way to be a lot smarter is, instead of meshing the entire model to a higher degree of resolution, is just mesh the areas of high stress, or high stress gradient to be more accurate. So I've used a mesh control tool to drill in on these faces. And, you know, with that result, I can get a very similar result to this with this much mesh, right? Just by localizing that. Other tools that you can use to help yourself prove that you have a good result, mesh quality plots. There is a result in the mesh quality called, there's a stress result called error. To run this. It's not an absolute error. You can't take it to the bank and say I'm 2 megapascals off here. It's an indication, but you will see the stress result somewhere in here. Energy norm error. Now it will point to areas where there are distorted elements, where there may be error, but if those don't correspond to a high stress, maybe you don't care. Like, this component is going to break here. If I'm 10% off up here, it's still not going to break there, at least for this particular scenario. So take it with a grain of salt. Applying mesh control is smart. FEA rules of thumb, we talked about that before. 2 elements across a thickness, 2 elements around a fillet is always good. There's a tool you can activate in the properties of a study. It's called adaptive mesh refinement. I'll show you where it exists. It's under adaptive. You can turn on. I recommend H adaptive. And what it will do is it will run a series of analyses, remeshing the model after every single instance. So it's just done one. It's going to remesh internally. Done a second one. See how many it's going to do. It's trying a third one right now. Right, and so it's presenting a result, but look at the mesh we get. Right, it's automatically refined it in certain zones. That's a technique you can use. Now that takes longer. And the last one here is a tool called the Trend Tracker. And what Trend Tracker does, it basically, every time you run an analysis, it saves the result out and kind of stores that data. So I ran my convergence study with Trend Tracker on, and it's kept 5 iterations of my model tracking across those 5 iterations how the stress changed. So this is the same chart that I presented, except the horizontal scale is not the horizontal scale is just iteration. Okay. So we're a little over time here. We've got a couple of questions that I'll address, and I've got nowhere to be, so you're welcome to hang around as long as you want. There's a good question here from Jason, who asks whether there's really any advantage to using assemblies versus multi-body parts. highlighting that in an assembly, I can grab this thing and open it in its own window. And that is certainly true. But otherwise, the software treats an assembly, from the analysis software treats an assembly and a multi-body part exactly the same. It does not. The stress analysis tool doesn't see any difference. It sees bodies and assemblies identically. And another great question from Jason, who asks, how do you deal with stress concentrations at a small corner? And that is a long-standing issue with finite element analysis. If you have a sharp corner, and this is going to fail, but it's okay, that is infinitely sharp, like this one I've just created here, especially if it's an internal corner with stress on it, if you keep refining the mesh, you'll get infinite stress. How do you deal with that? Well, there are a couple of techniques. What will happen in real life is, in real life, you will have a finite round. Depending on what sort of tool you've used to machine that, there will be some sort of round. If it's in place, don't suppress it out, model it, and then you'll get a true stress value. The other thing that will happen in real life is that corner will locally yield. So if you go to a nonlinear solver, you'll be able to model that local yield. The other thing that I do somewhat is, if I know it exists, but I just don't want to account for it, I'll take a stress result a couple of elements away from that fine corner and kind of consider that a local high spot. That is a tricky one. There is no good answer. There is no simple answer to that, fortunately. And then another question here from Sean. Thanks for the question, Sean, and feel free to share any other questions you have. What's a good rule of thumb for selecting a solver? Just to keep it simple, where is the solver? Here. I normally consider there are two different types of solver, and there's three more at the bottom here, but they're just variants of the others. Direct sparse will do a direct calculation of the software, great for multi-core, will use a ton of memory. And FFE Plus doesn't use very much memory, doesn't multi-core very well. So when you get to a very big model, FFE Plus becomes a lot faster, because you'll probably run out of memory. If you have a lot of memory and you've got relatively small models, you use direct sparse all the time. Large problem, direct sparse uses less memory. And these other two, the Intel Direct is pretty new. But in general, these are all validated so that you should get the same result. It's never the result that's in question, it's how long does it take to process it. There is an automatic option that will look at the size of your model, number of elements, and the type of contact you have in play, and pick one for you. And that's often a good thing to fall back on. Okay, that's most of what I wanted to cover. Sorry that we ran a little long there. But I would like to just finish up by highlighting some of the things that we have available in terms of analysis assistance. We're going to post this material to our blog pretty soon after we're done. I'm recording the presentation right now. And if you look at our YouTube site, our blog, or our website, you'll see a ton of information about analysis. And those are free of charge, available to everyone. Our customers on subscription service, you're welcome to call us on technical support. And we will be able to answer questions about the software, help you troubleshoot issues with your model, different things like that. So that's available. If you go to hawkridgesys.com/support, you'll see our dial-in number. You've got chat options. You can submit a web ticket or an email ticket. Lots of ways, and that's staffed by typically degreed mechanical engineers like myself. We provide classroom training, fundamental skills for the software. We have that in classroom, up and down the West Coast, in Minnesota and Toronto, basically anywhere we have a location. We also offer that in our online classroom that you can access from everywhere. We have a video course, a basic video course on the basics of simulation, so lots of options available there. And then if you want to go deeper, if you want customized assistance, we can offer mentoring, where we help you with your specific project one-on-one, defining best practices for your particular situation, or consulting, where we complete a project on your behalf. So all those are available. You're welcome to get in touch with us if anything there interests you. I'll stay on the line here, see if there's any other questions, but otherwise I really appreciate your attention. We had a great turnout today and a really lively question feed, so I thank you very much for that. Makes it more interesting, and I hope you found today useful and got something from it. So thank you all, and sit tight here for a few minutes.